Okay. So today we spent the whole time on one theorem, and maybe we will have to finish the proof on Saturday. This is called Compactness Geogram. It's a very, very general theorem in model theory, the starting point of anything. It gives us models of theories, and from this one we will be able to show these theorems which were needed for access theorem and Nullstellensatz, which was our original motivation. So we start with some language. Else. Okay, and fix a theory and the else sentence and then this theorem we want to show says that if any finite subtheory has a model, if any finite subset of T has a model, then T has a model. Okay, so out of nothing, we have to somehow construct this model. We have this assumption, and then somehow we have to get this model. So before this proof, I need several definitions, and then I will need 4 lemmas. So what are the definitions? Okay, I will try to keep everything on this board. So some of these definitions are important in general, some of them are mostly to prove this theorem, and they don't have such a big importance. The first one is important in general. So we say that phi is a logical consequence of the theory T. A sentence is a consequence of a theory if so this is tested, denoted in such a way. So this property is tested on L structures. So if for any L structure M, the following holds: if M satisfies T, then M satisfies phi. So today, all the time, there will be such abstract things. Okay, so get ready for that. First definition, logical consequence. Second, we say that the theory if maximal, if for any L sentence alpha, either we have that alpha is in T or negation in alpha is in T. Ah, sorry. Okay, let's do this. Yes. T is finitely satisfiable, basically if it satisfies the first part in this theorem. Finite subset of T as a model. And finally the last one, which is not very natural, but it will be crucial for the construction. T has the witness property. If kind of existential sentences, the truth of them can be kind of witnessed. So if for any L formula with one free variable, L formula alpha x, this is one free variable, for each formula there is a constant symbol. So it's very unnatural. Yes, usually we have few constant symbols, and here for each formula we have a constant symbol such that something happens, such that such a sentence exists x alpha of x, then alpha of c is in T. So you should think that, okay, kind of, for any formula which you may think is somewhere satisfied, there is a constant symbol witnessing it. Okay. So it's hard to give examples. This is sometimes called, they are sometimes called Henkin constants. So using such a constants, we will create our model, construct our model, and this is, it was Henkin who did it in such a way. So we follow his proof. So it's easy to give an example of maximal theory. So if M is an L structure, then this theory of M is maximal. Yes, because for each L sentence, either it's true or not, just the rule of life. Or not. And not is on a side which will be used, that never both. So this is again law of excluded middle, like in life. Yes. It cannot be true that today is Thursday and today is not Thursday. But one of them is true. Okay, now these four lemmas, maybe first one, how to organize, maybe here, maybe here.
Witness property.
Witness, yes. So, sorry. First, I don't want to. Yes, so you should think about it. Yeah, it's just what it is, but so if you have imagine you have a model of theory with witness property, okay? So imagine, you have a room here. Okay, then inside M, so let's say that in M, it is true that there exists X. Okay, so you can imagine that these are this. So this is like, so this is the set of M in M, non-empty, such that exists. So witness property says that in this set we have this constant. Okay? So C is here. CM, okay, if you want to see interpretation. But
Phi or alpha?
Alpha, sorry, yes. So you could say that the C depends on alpha, but I didn't want to put it.
It says it's not empty.
Huh?
It says that this is not empty, basically.
Not only. It says that if it's not empty, then its non-emptiness is witnessed by a constant from our language. Because usually it doesn't have to be like this. It's like in the language of ring, we just have 0, 1, so they don't witness almost anything. So it's an unusual situation. In real life, we don't have such things, okay? But it will be important in the proof.
And this should be true in any model.
If theory has witness property, then it should be true in any model of the theory, yes. But somehow, morally, it's not a very good, okay, but now we just want to construct some models. So this is just what happens later, kind of. But you should really think it's a very, very abstract property like this. And if you have some models, that something like this happens, okay? But actually, from this property, we will create a model. So it will go... Not a very natural, but now we start like we are, I don't know, bare. We have nothing, and we want to have the first model in our life, okay? And that's so sorry. Okay. The maximal should be obvious. So somehow everything looks kind of obvious, but to put things together and get this model is not so obvious. So assume to be finitely satisfiable. So now I connect the definition of logical consequence with just belonging to theory. Finitely follow and maximal. Okay, then if we have a finite subtheory and okay, if this finite subset of this theory has phi as logical consequence, then this phi must be in T. Okay, doesn't look strange, but it's really connecting two different things so far. This property and really belonging, being a part of theory. Okay, so here I will keep the statements, here I will do the proofs. That's my plan at least. So proof. Lemma 1. So assume it's not true. And we will find a subset of T, finite subset of T, which doesn't have a model, contradicting that T is finitely satisfiable. So assume not. So under these assumptions, phi is not in T. By this maximality, which is here, either this holds or that. So if the first thing doesn't hold, phi is not in T, the second must hold. Since T is maximal, negation of phi is in T, and now we will show that finite set, which is this delta and negation of phi, has no model. So take any L structure M, so since this phi is a logical consequence of delta, we have that if M models delta, then M models phi. So from this last comment, never both. Hence, if M models delta, then it is not true that M models this. So whenever this happens, this cannot happen. That means that together, delta and negation of phi, it has no model. Yes, because for any structure, if this holds, then this cannot hold. But this is a part of T. This is also a part of T. Yes, here. So this is finite and no model. Contradiction with finite satisfiability of T. Okay, not much, but we will use it many times to construct this model, this property. May look very, very obvious, but it's connecting two a priori different things. So actually now we construct the model in lemma 2, but we put more assumptions than in compactness theorem, and in next lemma we will kind of notice that we can always add these assumptions. So lemma 2 says that T is finitely satisfiable, maximal, and has witness property, then we can construct a model. And of the, sorry, I forgot to say something important in the beginning. Sorry. Kappa, sorry. Kappa will be, it's important also how big is the model. This will be important for applications. Okay, so this is maximum of Aleph 0 and cardinality of T, which is maximum of these cardinalities, has a model of cardinality at most kappa. Sorry, I forgot to write it, but that the model has bounded cardinality will be also important later. So in lemma 2, okay, we put more assumption on T and we get such a model. So T is finitely satisfiable. Is maximal, has the strange, so maximal is also a strange assumption. Usually we don't have such, okay, except such theories, we also they don't much exist in nature. Is maximal and has the witness property. Then he has a model, so actually of cardinality even bounded by cardinality of constants. Yes, but because of this witness property, there are lots of constants. So in this case, it's enough to bound like this. So here we construct this model, and in next lemmas afterwards, we will make sure we can extend the theory to one which is maximal and has witness property. And putting all together, this will be the full proof. Okay, so now is the construction. So this will be this construction by Henkin constants. So proof of lemma 2. Yes, so we have to construct this model from the constant symbols of the language. We know there are a lot of them because of the witness property. So we put some equivalence class on constants, symbols. So we say that C1 is in this relation with C2 if and only if the sentence is in T. Quite natural, okay. So in T, always their interpretations are the same. So in the model, they also have to be the same. So it's a natural thing to do. And now first we want to show it is equivalence relation. So let us see only transitivity. So take C1, C2, C3, three constants such that, such that C1, C2, C2, C3. So this means that this is in T. And this is in T. Okay, example is not so important. And then notice that it will be example of logical consequence, that if we have these two sentences, that logical consequences of them is that C1 equals C3. Yes, in any model, if C1 equals C2 and C2 equals C3, then of course C1 equals C3, because equality is transitive. So obviously this is logical consequence of these two things. So by okay. By this, and now we use lemma 1. We have a subset of T, which is maximal and its logical consequence. And lemma 1 and maximality of T. We get that C1 equals C3 is in T. So indeed, C1 is in the relation with C3. Okay, so this is equivalence relation on the set of all constant symbols. So now we define the universe of our model. Will be the set of the constant symbols divided by this equivalence relation. So the set of equivalence classes. Okay, so we have something kind of concrete. We have the universe, we have the set. Now we have to make it L structure, and then we have to check it is a model. So we have to interpret all these functions, symbols, relation symbols, and constants here. Okay, so we will put an L structure on M. So let's start with relations. How do we interpret this relation symbol? Okay, which has some arity.
Isn't M equal to C?
The set of equivalence classes of this relation in C.
Yeah, but it's like each set is like singleton.
No, not necessarily.
No, it may be. You may have such. If there are no such sentences, yes, but there may be. If and only if. In this theory, two constants are the same. May happen, yes. There may be theory in the language of ring saying 0 equal 1. So then.
Maybe some two different functions. The different formulas define the same constant.
Okay, I understand.
They have to be equal.
But here, even physically, this very equality must be in this maximal theory, okay? And then, yeah, but all of this is a bit hard to give examples. It's very abstract construction. But okay, you can imagine that later we will start from some normal theory and we will kind of artificially add all these constants, and somehow, because of the theory, some of them may be forced to be the same. So we have to divide by this. Okay. Yeah. So what is it? We have to understand what are. So for this relation, we have to say when an n-tuple of this equivalence classes is in the interpretation of this relation symbol. Okay, so take this. So we are trying now and take any C1, C1, Cn, Dn constant symbols. So claim 2 says that if they are, so these are like two n-tuples. Claim says that if up to equivalence relation they are the same n-tuple, then okay, then something good happens. Then we have that such a sentence. So this is a sentence, yes? If we plug to the equivalence relation symbol appropriate number of constants, it becomes a sentence. So this is in T if and only if the one with the equivalent n-tuple in this sense is also in T. Okay, and using that, it will be well defined. We will be able to define in a good way interpretation of R in this set of classes. So, proof of claim 2 will be similar. So it's totally symmetric, so one implication is enough. So assume that this holds. Okay, so by the assumption C1 equal D1, Cn equal Dn, it is also in T. So since but again, if we take all of it, if we take all of these n plus 1 sentences, which are in T, then it's a logical consequence of it that the sentence R d1 to dn. Because in any L structure, if really C1 equals D1 and Cn equals Dn, and R holds on C1 Cn, then because of these equalities, R must hold on D1 Dn. Okay, but this was a subset of T, which is maximal. So again, by lemma 1, this is in T. Which is what we wanted. So claim is proved, and thanks to it we can define interpretation of R. So can define. Yes, now we want to define this interpretation. So we want to say when such an n-tuple of equivalence classes is in this interpretation of R, so we define it exactly when this sentence is in T. And because of claim 2, it does not depend on the choice of representative here. Okay, so because of claim 2, this is really well defined. So these are the relations. Now, okay, let's do everything precisely. So question here. So everything is kind of natural, how you would think you should define these interpretations, but one should check it is well defined.
A little, can you?
Yes, sure.
A little slow down.
Uh-huh.
So what did we do? Our universe is the set of equals classes.
So shall we start from the end? We want to interpret this relation symbol.
Yes.
Okay, and this is the natural definition.
Yes, definitely.
That is the definition, but we have to check it is well defined. And this is claim 2, okay. So maybe the other way was, yes?
We know that the right hand side is in T because of the witness property, right?
Sorry?
The right hand side of the last equivalence.
Uh-huh.
Know that R, C1, Cn is in T because of the witness.
No, there's nothing like this here, no. We don't know if it's in T. It is just a definition. Okay, look at the full thing.
This is how we interpret
Yeah, this is... So maybe it's empty set. Maybe interpretation is empty, but still we want it to have be well defined. So we cannot have that at one represent. Yes, so see here, this is equal. This class is equal also D1 over this Dn over this. So this must be the same property. Otherwise, it would not make sense. So thanks to claim 2, it made sense. But still, maybe it's defining empty set. Who knows? But it's a good definition. Okay. Yeah, witness property didn't come yet. Now, for functions, witness property will come. Okay. Yeah, okay, you are waiting, right. So far I used these two things only, maximality and finally satisfiable, to be able to apply lemma 1. I didn't use yet witness property. This all may look strange, but then you see that compactness theorem actually has quite a powerful application. So somehow it's good to do this part quite precisely. So now formulas, sorry, it is function symbols. So take a function symbol. Can you see? and again of some arity n. Yes, so we want to interpret it as a function from nth power of this set of equivalence classes, again to the same set, somehow. So what's going on? Okay. Yes, now witness property comes. So take and now, so I'm saying what we want to do. So we want to define this f interpreted in M Yes, we want to find this value. This is the interpretation. And this will be the witness property. Tells us that there is such a thing which is good here. Okay? So we want to find this question mark. So now, since T has the witness property, yes, because before it was some property on the subset, but now we really need an element. Now we are not happy if there is some empty set. We really have to find some element. So this is the part when something has to be witnessed. By the witness property, there is C in C. And now what is the formula which comes in handy? Of course this one. Such that, what am I saying? Okay. Such that, such a thing exists X X implies is in T. So, okay, so maybe again I will slow down. So we applied the witness property to L formula. So what is L formula? Alpha of X. Yes, this one. Yes, this. I mean exactly to this alpha. Just, yes, because we are looking for this element. So we take the formula with one free variable, which is this value. And to this formula, we apply witness property. And formally, there is this witness. Okay? Yes, I may stop for a while, but somehow there is not much more than that. It had this abstract witness property, we assumed so, and we apply it to such a formula. So, by this, we get this C, such that such a thing happens. So why? So, of course, the value should be equivalence class of C. Okay, so now we have the corresponding claim 3. No. We skip the proof. Saying that this will be well defined. So for any C1, C, D1, Dn, D in C, if what? If and Dn and Fc1, Fcn, C in T, and Fd1, Fdn, then this value is in the relation with this value. So now, from this witness property, this possible value exists, and by claim 3, it is unique up to this equivalence relation. So.
T is equal to D is in T.
So in the quotient, in M, C is equal to D, this value. So using... So let me write the conclusion. We define that this interpretation Fm equals C if and only if this formula is in T. Okay, so by claim 3 is half well defined, but still such a C must exist. We need a value. So by witness property, there are such C's here. And by claim 3, they are equivalent. So this is...
C is not an element, by the way. I mean, it's not an element.
Mistake. Sorry. Okay. So this part used everything. To interpret the function symbols, we had to use all the assumptions, including witness property.